All right, so yesterday we talked about how to graph vertical asymptotes and horizontal, okay, how to find intercepts. Today our focus is going to be on the slant and oblique asymptotes. Okay, so they're either called slant or obliques. They are going to be linear functions. Okay, so if the degree of the numerator is one more, has to be exactly one more than the degree of the denominator, that's how you know when there is a slant asymptote. And it's all about the degree. So the degree is one more than the degree of the denominator. That's when a slant asymptote is going to occur. Okay, so to find the slant asymptote, do you guys actually remember this from last year, how to find it? We use long division. So there might be some musical stuff. Hey, so the asymptote is going to be equal to the quotient. Yeah, it does sound like there's a little hot noise. Okay, I thought I pressed pause on that. We'll listen to some classical today when we're working. Okay, so the asymptote is going to be equal to whatever your quotient is. And then there's too much noise outside in the court. Okay, when you are dividing, okay, the quotient is what is on top when you divide. Okay, so you're going to add the y equals to it. All right, that is better. Okay, so the quotient, like when you set this up, you have your polynomial, you have your dividend, and then the quotient is what you get on top. You are just going to set that equal to y. Okay, it is always going to be linear. So it's going to be of the form y equals mx plus b. And remember, we said the degree of the numerator is one more than the degree of the denominator. Okay, so they have a difference of 1 degree. That is why it is always linear. Okay, always linear because the difference is 1 degree. If you were to get x squared when you divided, okay, that would not be the correct situation to produce a slant asymptote. Okay, so just like horizontal asymptotes, the graph of a rational function, it can cross a slant asymptote, but that's not always going to be the case, okay, and it's going to be rare for us to see that. So we're going to observe the graphs of rational functions on the next page, and then we are going to write the domain and range and set builder notation. This is so you have a place to go to see the different types of cases. What we talked about yesterday is if you have the domain. Do you guys remember what's always excluded from the x values? Which ones in particular? Yep, the vertical asymptotes. Okay, the range is going to vary by case, and that's why we're going to explore those cases. Okay, so what I want you to do on the next page is I want you to say the domain for each of the cases on the next page. Okay, so you can do the domain for each of the cases on the next page. Okay, so you fill in the domains. If you're unsure about one, you can skip it, go to the next. Okay, so if we are excluding the vertical asymptotes, let's see where they are on the graph. Okay, so for our first one here, okay, they lightly just put these in with a line. We're going to make those more noticeable with the proper notation of the dash line for the asymptote. Okay, so this crosses at 3, this crosses at -2, so our domain is going to be x such that x cannot be -2 or 3. All right, now the next one's a little bit harder to see, but you can use what the lines are approaching to help you. So what does it look like? What x value are the lines getting really close to? 0. Yep. Okay. So remember when you have it on the axis that's a little bit harder to see. Obviously, if it's a black and white graph, you won't be able to see that. We're going to put that in. So x such that x cannot be 0. Okay. And then the last one, you can see these faint lines that go through -1 and 1. Okay, so then your domain is x such that x cannot be -1 or 1. And you can just put a comma between, that is fine. Okay, now for your range, if you have vertical and horizontal asymptotes, in this case the horizontal asymptote, look and see what your lines are getting closer and closer to. The lines are getting closer and closer to 0. So you have this horizontal asymptote here, okay? So when you have this, there's really 2 different cases because it can cross a horizontal asymptote. So we're going to write down both of those cases. So one case that we've already talked about is that it has to be less than or equal to wherever this maximum is. Notice that the maximum is not the same as the y-intercept here. Okay, sometimes they are the same, sometimes they're not. Okay, and then so it's less than or equal to the maximum, or y is greater than the horizontal asymptote if it doesn't cross it. Okay, there are cases where it does cross it. So if it crosses the horizontal asymptote, then y is less than or equal to the max, or you have to find that minimum value. Okay, and it would be greater than or equal to the minimum. Okay, so this only goes out to 7, so if it like dipped down as it continued out, you would find the min using that feature on your graphing calculator. Okay, so the horizontal asymptote, whether it crosses it or not, is based on what your horizontal asymptote is. Okay, and sometimes there would be no solution for the horizontal asymptote if you set it equal to the original function. And if there's no solution, that's when it doesn't cross. If you set it equal and there is a solution, that's where it would cross. That does take some extra work, so you are not going to have to do that algebraically. You're going to be able to find that on your graph. Okay? All right. And then for this one, you can see the slant asymptote here. It goes through 0, 0, and then each of these points is up 1 over 1. That's the slope. So your slant asymptote is y equals x. Okay, and then if you have these 2 curves, you're going to have a minimum and you're going to have a maximum. So that means your range, all the values are either below the maximum or above the minimum. Okay, you may notice it's similar to what you have here if it crosses the horizontal. And then we can see the horizontal asymptote in the last one crosses at 1, y equals 1. And when you have this, we looked at this yesterday, if you have a curve that crosses the horizontal asymptote and goes from positive infinity to negative infinity, we know that our domain is going to be what? All real numbers, yeah? Great. Okay, so those are the different cases you will encounter, so you can use this to help you when you are deciding how to find the range. All right, now we're going to identify any of the slant asymptotes for the following functions. So we're going to set up long division. Remember, when you're doing long division, you can decide if you want to put the placeholders in or not. Sometimes they're helpful, sometimes they're not necessary. I'm going to put the 0x in here. Okay, and I generally don't put the placeholder in here, but again, that is up to you. You know what, I'll do it for this one and not for that one, just so you can see the process, okay? All right, so the first thing we do is we divide. 3x cubed divided by x squared. So 3 divided by 1 is 3, x cubed divided by x is x. Okay, if you're ever unsure what that number is on the top because you are setting up fractions, sometimes it'll be a fraction, just make sure you set it up as division and go from there. So 3x times x squared is 3x cubed plus 0x minus 6x here. Change your sign, change your sign, change your sign. Okay, so that should cancel. This is going to stay the same. 0 plus 6x, and then I drop down the positive 1. Okay, and my next step, again, I'm dividing. So negative 4x squared divided by x squared is negative 4. These should match when I distribute. Negative 4x squared and negative 4x squared. A negative times a negative is a positive. I'm going to switch the sign, switch the sign, switch the sign. So I get 6x minus 7. Now the degree is less than the degree of the divisor. Okay, so when you are writing this out, you're going to write y equals 3x minus 4. Okay, so when they say to identify any slant asymptotes, we do want to just make sure the degrees are 1 apart. So the degree of the numerator is 3, the degree of the denominator is 2. So whenever this is 1 more than the denominator, you know that it's going to exist. Okay, because you are going to expand and have some where you're going to have to determine if there is one. Okay, same thing here. This is 3, this is 2, so there's definitely going to be one. All right, and then you can do this one without the placeholders. Why don't you give that a try? And then once you've done that, you can go to part C, steps 1 through 4, the same as yesterday. All right, so when you divide, you're going to get 2x. That gives you 2x cubed. 2x times negative 1 is negative 2x. This becomes negative. This becomes positive. And then the degree here is less than that, so that's your remainder. So your slant asymptote is just y equals 2x. All right, so now we are going to graph. We are going to review those steps from yesterday. It is going to be the 1 through 6. We're just going to add on the slant asymptote. So step 1, we are going to factor. So look for your GCFs. You can take an x out of the top, nothing to factor in the denominator, and then we're going to find our x-intercepts. Okay, we saw a couple examples yesterday where you didn't have an x-intercept or a y-intercept because something was undefined. That's the same thing if you get something that's imaginary. Imaginary values do not exist on the graph, which is why we can't see imaginary x-intercepts when we look for them. So the x-intercepts are formed from zeros of the denominator. So if you, zeros of the numerator. So if you've already factored the numerator, you can set each factor equal to 0. Okay, so we're putting those there. Nothing to solve for here. This would be -2. And then on your graph, they would be 0, 0, and -2, 0. That's what you're going to be graphing. For the y-intercept, you can plug in 0 for x. So if I plug in 0 for x, 0 squared plus 2 times 0 is 0. 0 minus 1, -1. Can you do 0 divided by -1? Yeah, 0's on the top, it's just 0. Okay, so that means your y-intercept is 0, 0. So if you get 0, 0 for x, it's going to be there for y as well. Okay, after that, we are going to find the vertical asymptotes. So for the vertical asymptote, you're going to take the denominator, set it equal to 0, which is going to give you x equals 1. Remember from yesterday, we do want to keep that x equals because it's an equation of the line. For the horizontal, we compare degrees. Okay, so the degree of the numerator is greater than the degree of the denominator. Okay, 2 is greater than 1. And math and what? Just kidding. Okay, so there's no horizontal asymptote here. When that happens, when you have no horizontal asymptote, the degree of the numerator is greater than the denominator. So this is when you have to ask yourself, is there a slant asymptote? You only have to ask yourself that if there's no horizontal. Okay, so if there's no horizontal, there's possibly a slant. It just depends on how much bigger the numerator degree is than the denominator. Okay, so yes. It's greater by 1. That's how we know there's a slant asymptote. So then we get to do long division. So when you're setting up your long division, it's x squared plus 2x divided by x minus 1. Okay, so I want you to go ahead and do long division. And then you can start setting up your graph. So putting the asymptotes on there. so when you divide, you're going to get x, and then we're going to distribute. Make sure you change the signs, circle to show your change. And then 3x is linear, x minus 1 is linear, the degrees are the same, so I can keep going. 3x divided by x is a positive 3, so I have 3x times negative 3. You change the sign, you change the sign. There's nothing to add this to. That's because this is going to be your remainder. Okay, so then your slant asymptote is y equals x plus 3. Okay, so when we start our graph, let's start by putting on the vertical asymptote. Oh, actually, before we even do that, we should check the graph, right? We want to make sure that when we're graphing, it can fit in a 10 by 10. If not, we need to adjust our window. Okay, so when you plug this in, plug in the original. That way you have it with your parentheses. Okay, so either plug it into your graphing calculator, or if you want to use Desmos, you can use Desmos. And when you graph, if you press the zoom standard, that means you can have it in a standard window, that 10 by 10. For this one, I can see those two branches. Okay, it might look a little bit better if I zoom out, but you can work with this. Okay, so I am going to go by ones here. If you wanted to go by twos, you absolutely could do that as well, and it would show more of that branch. Now, when you're putting on a slant asymptote, this is just linear. So we start at the intercept, 1, 2, 3, and then we use the slope, which is up 1 over 1, up 1 over 1. So if it's just up 1 over 1, you can do that pretty easily with your dashes. Okay, if it's not a slope of 1, just feel free to put the points like I showed here, and then connect with a dashed line. And then, of course, we are going to label that. All right, and then we already have some points to put on there. We found 0, 0, and we found negative 2, 0. We just want to use our table to find some points that are going to fill this in to help us make an accurate curve. I do recommend going by a half so you can see what's happening in between there. That can help so that you don't accidentally run into this asymptote, because you do not want to cross a vertical asymptote. So at 1/2, I'm at negative 2.5. Okay, so I'm going to put that there to help me with the curve. And then I'm going to look and see what's happening in between these two. Okay, so at negative 1, I'm at 1/2. Okay, and then I'm going to look a little bit further out, let's see what's happening. Maybe at negative 5, so 1, 2, 3, 4, 5 is negative 2.5. And then maybe I'll just get another one. Negative 9 is negative 6.3, so 1, 2, 3, 4, 5, 6.3. Okay, so that should be enough to give you a nice curve to follow. Just if not, sometimes we get a little sloppy and we tend to run into some things that we do not want to run into. Okay, and that's why I usually do it in pencil first as well. All right, and then I'm going to create this top branch here by looking at some values that are greater than 1. Okay, so 1 is an error. That's a good sign because that matches up with what I have. This 1.5 is up at 10.5, which is about there. I'm going to put that on so I can see where I'm going. And then at 2, I'm at 8. At 3, I'm at 7.5. At 4, I'm at 8. at 6. 1, 2, 3, 4, 5, 6. 9.6. Okay, and again, I just do that to help me make this curve. Okay, so now you have each branch there. And once you have each branch, you're ready to do the domain and range. Okay, if you're not sure what to do for the range, use what we did at the beginning of today to help you. So this graph looks a lot like our second situation, which is where we have to find the max and the min of each of those curves. Okay, the domain is nice because you have a set pattern every time. So for your domain, it's x such that x cannot be 1. That is your vertical asymptote. Okay, and then based on our situation here, we have to find the max and the min. Okay, which I can do very easily from my graph. I just have to go to second calc. It's on the minimum one first here. To switch it over, you just have to arrow it, and then it will jump back there, like jumps over the asymptote and goes to the other curve. So it's asking me left bound. So I make my bounds just pretty large, so it will find the highest point there for me. We can go ahead and round to the nearest hundredth for this. So it's y is less than or equal to, and if I round this correctly, I would get 0.54, and then I'm going to find what my minimum value is. Okay, so whether you're using your graphing calculator or decimals, double check to make sure you're comfortable finding those points. Okay, sometimes I think, oh, I've found the max and min 100 times before. I don't need to do that again. Okay, but it's good practice to make sure we know where those values are, because you do have different situations with these kind of graphs. So when you go to the minimum, that is number 3. So it's on this curve. I'm going to arrow to the left because this is to the left here. Okay, and then I'm going to tell it, hey, find the lowest point between these two things. Okay, and it will do that. Okay, so you should get 7.46 if you round to the nearest hundredth. Alright, so you are going to finish the assignment from yesterday. Your graphs do need to be on graph paper. I have graph paper available if you need it.